That's what we have done so far. What we've done after solving the second order differential equations, we came up with the wave equation solution, which was in the form of the electric field and the magnetic field in the form of sines and cosines in the cross section and propagation in the z direction. And the propagation in z direction will only take place when we exceed the critical frequency of that particular combination of M and N. For each combination of M and N, you have a critical frequency below which you have cutoff. Above that frequency, you have propagation. So we are now continuing our discussion of the propagation region, the region for which the frequency exceeds the cutoff frequency. For any given M and N, you will have this kind of situation. Going back to the basic Maxwell's equations, the 6 equations that we have here, curl H is equal to, curl E is equal to, we spelled those out and rewrote them, manipulated the terms such that we wrote Ex, Ey, Hx, Hy in terms of Ez and Hz. Alright? That was simple manipulation here that I didn't quite do in the lecture, but I told you it takes a few steps, and you will see it in the notes that I'm going to send you. I'm working on that part. I'm going to put it on Scholar fairly soon. So we'll see how we got from here to there, all right? It's a couple of steps. No, it's not that big a deal. But anyway, we have those equations which tell us that if you have the Ez and H sub z, I can get you the rest of the field parameters. Yes, we can get them from here, but we'll have lots of unknowns, because each time we solve a differential equation, we'll have to assume constants. And those constants are interrelated, right? So if you don't have the interrelationship, you will just assume constants, and you have lots of unknowns. Well, these are the interrelationships, right? These determine exactly how Ex relate to these two. So I won't have to write Ex in the form of a constant sum sine plus a constant on cosines, etc., right? I don't have to do that, so I can just go to these. Now, we have the Ez solution and the Hz solution. We did this here in the lecture, and I showed you the boundary conditions, how we arrived at those. This is another step here that is done similarly. If you apply the boundary conditions here as well, you get that kind of expression. I have a mistake here. This should be a cosine. Okay? A cosine. The E field gives you sine, and the H field gives you cosine. And we arrive at those expressions simply by applying the boundary conditions, assuming that the metal is perfect, and a perfect metal would give you, or a perfect conductor will give you 0 tangential fields. The electric field has to be normal, no tangential field. And we use that, and we get these two expressions. Now that we have those, we can go back and get the Ex, Ey, Hx, Hy, and we have the entire field solution. But instead of doing that for the whole thing, we decided to break our solution into 2 categories, 2 groups. And the general solution will be simply the sum of the 2, right? So it's not like I take a special case. I'm just breaking my problem into 2 problems. I solve each one individually and add the solutions, right? So there's nothing that we assumed here that takes away from the generality of the solution. The solution is still as general as it could be. So we call this kind of situation without the H sub z as the Tm modes, and without the E sub z as the Te modes. And simply because if you don't have E sub z, that means you only have Ex and Ey, and these are transverse to the direction of propagation. So it's transverse electric. Likewise here, if H sub z is 0, then you have Hx and Hy And again, these are transverse to the direction of propagation. So that's transverse magnetic. All right? The general solution is simply the superposition. So if you wish, the general solution would become the sum of these two, or the superposition of these two. So you can have situation where you have both EZ and HZ, and neither is zero. Now, if you have both EZ and HZ are zeros, you get what we call TEM. All right, so let me write on the side here, TEM would be EZ is equal to 0 and HZ is equal to 0. And that doesn't happen inside waveguides. It only happens in plane waves, right? You cannot have TEM in waveguides. That is a plane wave propagation, which we've done before in 3106, right? The previous course, undergrad electromagnetics. And you can prove that that doesn't exist here, okay? You can prove that it does not exist here. Right there we can see it. If both E sub z and H sub z are zeros, all these fields will be zeros right away, right? So it's easy to see, all right? So if that's the case, Dx equal Ey equal Hx equal Hy is equal to 0. By the way, that kind of writing we always do in mathematics, and we kind of are careless when we write that, all right? Because they are not really equal, right? They are all equal to zeros, right? Rather than, so when you write that, you have to be thinking in the background, I don't mean it, right? I really mean that each one of them is zero, infinitesimally small, okay? So that's a careless way of saying that they vanish. All right, so we come here now and apply this to the individual cases. And if we have E sub z is equal to 0, which is this case first, the TE modes, and we have those, we can put them in. That means your EX is equal to, let's write them all. Let's write EX and HY next to each other, and H and EY and HX next to each other, because there are similarities here. First of all, E sub z is 0, so that term disappears. And now the EX will have the derivative with respect to y. The derivative with respect to y will give us a sign here, so we have a minus sign. So we still have a cosine m pi x over a, and we have a sine n pi y over b, and we still have the hz plus e to the minus j beta, etc. But the coefficient here now is, when I differentiate, I have a minus j omega mu over k sub c squared. I have to squeeze that in. Let me give myself some more space on the left here. Dx equal minus j omega mu over k sub c squared I have a minus sign from the derivative that becomes plus, and I have n pi over b. N pi over b. Okay, that's your EX. Your HY is identical here, but you have minus j beta over kcc squared. So the HY minus j beta, I'm not writing the subscripts, over kc squared. And I have n pi over b again from the derivative. Same thing, cosine, sine, etc. Let's next write the EY. So I go to the EY and I have omega mu over kc squared. Omega mu over kc squared. And I have the derivative with respect to x, I have m pi over a. And again, a minus, and I have now sine m pi over a cosine n pi over b hz plus e to the minus j beta z. And finally the hx, what do I have? Hx right there. I have a minus j beta minus j beta, so I have a plus j beta because the derivative will give you a minus m pi over a again, and I have kc squared sine cosine exponential. Likewise, I can do the same thing here, right? Now we notice that these are similar to each other, so the ratio here, dx over hy, is equal to omega mu and we decided to put a minus sign here if you remember. So get rid of the minus. Omega mu over beta, right? And over here, Ey over Hx is equal to, again, omega mu over beta. And we call this one here eta guide for the TE modes sub Mn. That's eta guide for the TE modes sub Mn. Beta guide. So if I divide eta guide Mn for the TE modes over eta in the material, plane waves, let's write TEM for unguided, right? The unguided situation. This one here is omega mu over beta guide divided by omega mu over beta, which comes to be beta over beta guide. If you do the same thing for the TM modes, you will discover that eta guide TM modes is the opposite. It is going to be equal to beta guide over beta. I don't have to show it because you can tell it on the map.
For EY, should there be a J instead of just the one?
They're all J's, right. Thank you. Let me write that in a different color so I fix my errors and you know that these have been corrected. And there was another error here, that was a cosine.
There's something else I was wondering about in EX at the end, negative J beta Z at the very end of EX.
This one?
No, at EX at the top.
EX.
Yeah,
okay.
at the end of the equation.
Yeah.
I think it's negative J beta Z, right?
Yeah, I wrote that dot, yeah.
Oh, okay.
Okay, beta guide Mn times C. You're right. Okay. Beta guide Mn times C.
Are the HZ pluses and EZ pluses just constants on the right side?
Exactly. Now, what we mentioned last time is we're dropping the HZ minus and the EZ minus, okay? And the reason for that is simplify the expressions, and we're not losing the picture here. Because basically, you have yourself a wave that travels this way, that's a plus wave, and a wave that travels this way, that's a minus wave. And the minus wave relates to the plus wave by determination. All right? So what we've done in the transmission line chapter, if you remember, we called gamma of z, we can write it here as m and n, is equal to the minus wave divided by the plus wave. If we do that, that means we can write our expression. Our general expression was e to the minus j beta guide z m and n plus ez m and n again m and n minus e to the plus j beta z guide mn. This one here can be rewritten as ez plus e to the minus j beta guide m and z times 1 plus gamma. Right? So if I drop this term, I'm not losing much because I can always add it in. Anytime I need to put that in a non-matched situation, I can just put the 1 plus gamma expression in. Right? So I'm just dropping it for the sake of convenience. At the same time, I can always put it back as needed. Right? So that coefficient is there and talks about what happens here. Now, to get the, now we still have the EZ plus and HZ plus, right? These have not been determined yet. We know that there are two boundary conditions. One boundary condition at determination that gets you your gamma, and the other boundary condition at the source here. The boundary condition here is the one responsible for getting these two. So the two boundary conditions finish the process of determining the unknowns. All right? Source and termination. And usually we don't worry much about these two because we are mostly concerned about matching issues rather than level, as it turns out in most applications. So these are level quantities that are determined by the source and its matching. The ratio here determines determination and its matching, which is the gamma. And the expression here all can get you 1 plus gamma whenever you need it. You can simply add 1 plus gamma anywhere, 1 plus gamma, 1 plus gamma, and you get your final expression again. Okay? So we saw the impedances. Again, the impedance in the guide is different than the impedance in open media. Guided versus unguided. And in the opposite situation, it's the other way around. Obviously, this is equal to lambda over lambda guide. And this one here is equal to lambda guide over lambda. So if you want to plot the impedances here versus frequency, F sub C Mn, I'm going to do, that's eta unguided. If it's lambda guide over lambda, we know lambda goes to infinity at the cutoff frequency. Right? So we are up here coming down to asymptotically to that. The other one will start for the opposite. If that's infinity, so that becomes a 0 and goes up. So this one here is for the TE modes, and this one here is for the TM modes. This one here is Z eta guide MN. And again, that repeats for all the cutoff frequencies. whichever cut frequency you have, your other curves.
When you say the unguided, you're saying 377 ohms, is that right?
Well, 377 is for free space, all right? When epsilon and mu are epsilon naught and mu naught, right? But if you have a material, then you have epsilon relative and mu relative, that you modify the 377 by that number. Okay? All agree? Now, for the TM modes, as it turns out, you can't have neither M or N equal to 0. If M is equal to 0, your E sub Z is equal to 0, right? And we already have H sub Z is equal to 0, that means everything is dead. If N is equal to 0, same thing. So the lowest order mode here is 1, 1, right? If you want to write the modes here, different color. So the TM modes, if you want to write the M and N as a tabulation, the lowest one would be 1, 1. If you want to, let's start here, 0, 0, 1, 0, 0, 1, 1, 1, etc. Right? All these will yield 0. This is the lowest order TM mode. For the TE, it's a different story. For the TE modes, we said 0, 0 are not acceptable anyway, so we'll start with 1, 0. M, N, you can have 1, 0, you can have 0, 1. What can exist? Next would be 1, 1, or 2, 0, or 0, 2, or 1, 2, or 2, 1. Now, which one comes first? That depends on your A and B. To determine which one of these come first, will this come first or that come first? Okay? All these will depend on A and B. Now, you can sit down and do a table like this, go on an Excel sheet and do all that, and then get those numbers, which is the F sub C, and then sort them out. Or you can do it graphically. Let me show you the graphical method. I need to do some erasing. So I'm going to do this board here. F sub C M N. You develop the expression for F sub C M N it turns out to be C phase velocity Mn, no, not Mn anymore. Well, if you wish, Mn divided by lambda Mn, right? Let me get it from another expression instead of reinventing the wheel here. Well, let me just write it from first principles. It's always easier to derive these things and memorize expressions. It's when omega CMN squared mu epsilon is equal to kx squared plus ky squared, which is m pi over a squared plus m pi over b squared, right? That's the critical frequency. And kx squared plus ky squared is equal to the k squared. Okay, in this case here, omega sub c mn squared is equal to 1 over mu epsilon square root of m pi over a squared plus m pi over b squared. So make this an f sub c mn, divide by 2 pi, the pi cancels out, you get 1/2 here, and this one here is c unguided square root of m over a squared plus n over b squared. That's much easier than memorizing. All right? Suppose we have free space, just for the sake of simplicity. If you wish, that can be written as C naught over square root of mu r epsilon. Okay? Just to be very clear about C unguided. So what you do is you draw a coordinate system like this, and you label this as m over a, and label this as n over b. And I'm going to take this in the denominator here. So f sub c mn divided by c naught over 2 square root mu r epsilon is equal to the square root of the x-axis here, your let's call it horizontal axis, plus your vertical axis. Okay? So you go units of m over a. 1, 2, 3, 4. These are units of m over a. And m over b, since b is smaller than a, right? We usually put the a as a bigger number and b is a smaller number. Then the units are going to be longer here. That's 1, 2, etc. And then draw your grid. This corresponds to m is equal to 1, m is equal to 2, m is equal to 3, m is equal to 4. This corresponds to n is equal to 1, n is equal to 2, etc. Get your operating frequency and change it. Operating frequency that much. Right? This is your F operating divided by C naught over 2 square root. So the radial is going to be your F naught divided by square root. If you are operating here, then you are below the cutoff frequency of both, and that means you have cutoff. You keep increasing your frequency until you get here, you touch the critical frequency of this mode here. That's the beginning of propagation for the M1 N0 mode. So here is the beginning of 1 to 0 mode. You keep increasing, and who knows whether you reach this one first or reach that one first. In the diagram I'm drawing here, you're going to reach that one first. So that's the 0-1 mode. Let me get a third color. If I do this one here, I get now the 2-1 mode. I'm sorry, 2-0 mode. If I go to this point here, let me use a third color. I get to the 1-1 mode. That's your 1-1. That was, the yellow one here was a 2-0. And the blue one here was a 0-1. Right? That's 2-0. And this one here was 0,1. And this was the 1,1. And I had this one, I'm going to make this white, which was the 1-0. So you can find out which mode comes first, right? It's obvious that you will get to this mode here before you get to that. If my drawing is right. So you may get the 2-1 before you get to the 3-0, right? So the radial dimension is your frequency scale, and it's equal to the square root of these two, which is the horizontal and vertical. That diagram is useful if you want to do it graphically. Like I said, you can always do an Excel sheet and sort out your frequency, cutoff frequencies after the substitution. You can tell which one happens first. But by all means, it's obvious that the 1-0 is going to happen first, assuming that the horizontal is wider than the vertical. If A is greater than B, then TE 10 is the lowest F sub C of all. The next one could be, like we said here, the 2-0 or the 0-1. Next would be the 2-0 or 0-1. Let's say the cutoff frequencies of all these three frequencies here. So F sub C 10 is C over 2 square root of mu r epsilon r. And the square root here gives you 1 over A. Right? M is 1 and N is 0. The F sub C 0, 1 will give the same exact thing. And then you have 1 over B. The F sub C 0, 2 or 2, 0 will give you C0 over 2 square root of mu r epsilon r and 2 over A. If this A is determined, then obviously this one is going to be twice as much, right? For a given A, this one here is twice as much. But this one here could be anywhere before or after. So if you want to increase your guide bandwidth, what do? you want to push this to be after. Because, like we said, 1 0 is right here, 2 0 is twice as much. Can't control that, right? But the 0 1 could be here or could be there. So obviously I prefer it there to increase my bandwidth. If I want to push that there, that means I want to make this greater than that. So I want to make 1 over b is greater than 2 over a. That means a is greater than 2b. So that's a rule for rectangular waveguides. We always try to choose a greater than 2b to maximize the bandwidth, or equal at the worst case. So we can say equal. You'll find, some waveguides are designed with a is equal to 2b, and some others are designed with a greater than 2b. The X-band waveguide that we talked about, which was 8.2 to 12.4 gigahertz, if you remember that, have this one here sitting at 6.5 something, and this one here is going to be 13.1. And what we do is we choose the A is 0.9 inches and the B has 0.4 inches. You can see it's greater than. We chose here greater than. Alright? That's the standard waveguide, the one that you'll be working with in the lab. In fact, A is equal to 2.25 B. Right? So anyway, we have determined that this one here is a dominant mode. Where was it? I erased that. No, it's still written here. So I want to go back to the dominant mode and see what the fields look like. All right?